All right, guys, so we're here in the lair of Steve, and this is a huge shop. This is a big operation here. Steve is just undergoing monumental work here every day. So we're gonna start with the first stage, the materials. There you go, you have some stock material there. And we're gonna start with the first step. Steve, please walk us through it.
So basically our process is we determine what the drive shaft needs to be. We go back, we select our piece of material, our piece of tubing, whether it's steel or aluminum, seam tube, DOM, you name it. We've got all of it available and on hand. It's not very often that we don't have what we need in the moment. And then once we select that piece of tubing, we bring it up to our horizontal bandsaw where we are gonna measure it out, and we're gonna cut that tubing about 1/8 of an inch longer than it really should be. That way it allows, if we get a little wander in the saw blade or something like that, we don't have any length issue. After it's physically cut, we put it into our tube lathe, and that's where, on the lathe, is where we can exact the length. We can get it to within a 32nd of an inch. We build all of our drive shafts, finished product, to be within a 1/16 of an inch. I personally target a 32nd in the lathe, is the way I go about it. So this is a great example of a NASCAR drive shaft.
There you go.
That we're shortening for one of our customers. They wanted a 1/2 inch taken off of it. It's a 4-inch 065 wall tube. We cut the end off, and then we will go through, square it up, straighten it, chamfer that end so that we can press a new end into it, and then it'll go up to our weld process.
Is this a chromoly?
That is just a DOM.
Just a
4-inch DOM.
And, sorry, maybe you mentioned that at the beginning. And what is the series U-joints that this uses?
Those are 1350 solid body U-joints.
Awesome.
The unique thing about this drive shaft is it's got our own custom manufactured ends. So the ends that we put on it and weld into place, they're roughly 1.5 pounds lighter than what would be used in a standard, Dana or Neapco off-the-shelf product.
Oh, wow.
We had investment casts done. We did FEA, we did structural testing, we did you name it to develop them. And we've been manufacturing those now for almost 20 years.
Wow, that's a great track record with it. So it comes to this machine, right? And here you would walk us through the step of what you do.
So what we'll do is, it's a big hollow spindle lathe. We can fit a 5-inch diameter tube through it. We'll chuck it up into the lathe, and then its operation just spins it right around just like you would imagine. And we can take our tool and then take it in and exact the length. We can cut on the tubing to get the length exactly where we want it to be.
Excellent.
As needed for the measurements, so that the stack up, the finished product, gives us our target length.
Absolutely.
Yep.
Very good. And then where are we going to go next?
After we go through that exercise and get those pieces, we will bring it up here. And I've got some staging for an aluminum drive shaft. So these are the aluminum weld ends.
Right.
That you saw in the 2-piece shaft.
These
that
are
it's
Sonex,
up there.
yeah.
Sonex manufactured. Yeah. They get positioned into our press. So what we do is we take the aluminum weld end. It is located with a couple of large pins. And then our piece of tube goes in the center there. The other end gets the same weld end.
Right.
Like this.
So this is a positioning fixture.
And it holds the phasing of the universal joint. So that they stay in phase. They're in alignment with one another.
So you don't end up with the vibrations, yeah.
Then there's a hydraulic press at the one end, and it pushes those ends in.
Into the tubes.
To the tube.
Very good. So yeah, this is one way that would allow you to align them perfectly without very little error, I would say.
Yes.
Yeah. I've always wondered how shops do this with shafts, what fixtures they use, but this is nice to see in person. Very good. So
And
then you've inserted the yokes into the shaft.
we've got the ends in. We bring it over to our build table, where we would fit in this case, a slip yoke and the rear flange into it. So these will get put into the weld yoke and fit. The universal joints will be fit so that they're snug, but yet, and you can see it takes a little force to move that.
Yeah.
That's what we like to see, because that's going to give us a better balance. Once that entire assembly is now hand fit together, it moves over to our welding operation.
All right.
And you'll see around me, we've got all kinds of slip yokes, universal joints,
Oh, yeah.
weld yokes,
I-
flanges, all the pieces that we need.
I remember when I first came to the shop and I had the Sonics adapter for the one that we're using right now on the shaft, and he said, "Well, I've got like a whole bunch of them on the shelf already," and he had the Sonics adapters for the V2 and a lot of other vehicles. I mean, you guys have to really walk through the shop just to understand the breadth of the parts that Steve keeps on hand, so that there's minimal weight when he's making his orders.
After it's hand fit together, we bring it up to our welding station. And our semi-automated welder, we have a MIG welder that does steel and a MIG welder that does aluminum. We set the drive shaft into our two weld heads. Depending on what the ends are, we hold the drive shaft just like it would be held in the car.
Right.
Whether it be by the slip yoke, the CV joint, the flange, the rubber coupling.
So a natural
gets held
situation.
that same way.
Right.
We align it and we check run out on the entire drive shaft. We're looking at run out at the front interface and at the rear interface, and we're correcting that before we weld. And then we use our weld, the strike of the arc, and that initial heat to pull it favorably when there's small amounts of run out. So that
Right.
we try and minimize the run out in
from
the
the
drive
get-go.
shaft.
Yeah.
From the very first time that we get an opportunity to influence it.
Very good.
And this is a typical Monday morning weld rack where we've got 5 NASCAR shafts that are headed for an Xfinity team.
Yeah. These right here.
2 of which happen to be, I believe it's these 2 that are going to Junior Motorsports, and the other 3 are going to Homer Friesen Racing, a truck team. 2 drive shafts for Silver Sport Transmissions, a Tremec Elite dealer. One happens to be going into an older Mopar because it's got a 7290 rear U joint, and I think this is going into a GM, probably a Camaro or something like that, that's getting a new Tremec transmission. A couple of offshore boat shafts for the guys that won the Class 1 World Championships last year, MCon Racing. They're a very good customer for us, and they needed a couple of backup drive shafts for their primary ones that we've already rebuilt and have over at the balancer. And then this is a custom Corvette torque tube drive shaft.
Yes, it is.
Using the rubber element or the rubber couplings at the end. We had to cut it down in length, and then we've high-speed balanced it.
So what's happening with this Corvette? Why did we end up needing this custom?
This is actually the torque tube, and the entire drivetrain is now going into an old Firebird.
Oh.
So a 68 or 69 Firebird is going to have a full running
That's a wicked project.
Corvette driveline. Yeah.
So, not many people can do this. Not many people can do this. This is very impressive.
After it goes through our semi-automated weld process, and this is typical of what our welds look like after it's been welded.
Let's do a close-up on that. Very,
The
very
aluminum weld and
Very
our
clean.
steel welds look very much the same when they're all set and done. It comes over to one of our 2 high-speed balancers. We've got Balancer A, Balancer B. I'm going to take you down to Balancer B in the moment because we have got tooling galore set up over here. Just so happens that another part, the part that's in the balancer right now happens to be for Junior Motorsports. It's one of his 4-inch steel drive shafts.
Which vehicle specifically is this going into?
The Xfinity Series NASCAR.
Do you know which specific vehicle? So when somebody sees it on TV, it says that's the one that has this.
I do not know what car number it'll go into.
All right.
I don't know what car number. They don't traditionally tell us that, but and a lot of times they don't even dedicate them to that. They just keep track of mileage on them, how many races it's been.
They use probably the same drive shaft, so there are multiple vehicles, so they just order a bunch of them.
It's based on
guys.
setup.
That's why we don't know.
Yep. So, but then I mean, we've got all this different tooling where we can.
So at this stage, the drive shaft has already been welded. Right?
This one has been welded, and it has actually been high-speed balanced.
And high-speed balanced.
Because I see the balance weights are being held in place by some tape right now.
Temporarily, yes.
Because what we're going to do is on our racing drive shafts, we TIG weld all of the balance weights to ensure that it cannot come off.
The best possible way to weld it.
Even though it goes through a lot of vibration, it goes through a lot of shock loading.
Gotta play it safe.
During the course of 2 or 3 races before it ever gets rebuilt, it just guarantees 100% that balance weight will never come off.
Very good.
So, and again, you can see where we've swallowed the slip yoke just like the transmission would hold it, and it's being held in our tooling. We've put the rear U-joint into effectively a machined pinion yoke that again holds it just like it would be held in the vehicle, and that's the way we balance it.
That is
so
a
that
very
we
good
get
way
the
to
best
do it.
balance that we possibly can.
That makes it as realistic as a real world scenario gets. And there's the machining you've done here on the side.
That is, we do that so that we can set the C-clip grooves based on that, and it gives us a nice flat surface in which we press those the universal joints in.
Makes sense. And the other balancing area, you want to talk about that?
The second balance machine is oh, you mean the one over here or this one?
That one over
Oh, the second balancer is identical to this.
Okay.
The big difference is it has a resin-filled base. So this balancer weighs roughly 12,000 pounds.
Wow.
Grand total. That one's about 15,000 pounds.
Just to ensure that there's
to make that base as dead and stiff as humanly possible.
That's not a factor a lot of people think about, at least people on my knowledge level. Yeah.
So most our balancers are on a stiff suspension. And what it is, it's roughly a 1/2 inch thick plate, C plate, that is allowed to vibrate with high speed vibration or energy being put in from the drive shaft.
Right.
Most people have soft suspension, so it vibrates real easily. And that's why they can't do high speed balancing, because you can't run it at high speed.
That's a big factor.
Yes.
Okay.
Yes. And one of the big advantages of that is outside noise doesn't influence the balance measurement.
Yes.
If I'm running the high-low and somebody's running the balance machine at the same time, that vibration doesn't
even register.
Yeah. As well as the natural frequency for the drive shaft is well below the natural frequency for what the machinery is.
That's very good. See, this is a whole science. A lot of people, I guarantee you, have not thought about this aspect, the stiffness of the machine, the suspension on the machine, the dampening, the isolation. This is why this area, you just can't get into it. There's a huge barrier to entry. So much knowledge and experience need to.
It's very difficult. And these machines are $300,000 to buy something like that in the marketplace today. So they're pretty unique.
Oh yeah. And probably a lot of the manufacturers that do these machines, probably, who knows, a lot of them have gone out of business a long time ago.
That's right.
I know a lot of industries where there's specialized equipment that can no longer be purchased anymore.
Yeah. Yeah.
Even in my industry.
Yeah. Yeah.
That's true. So the two-piece drive shaft that we made, was it balanced on this machine or on the other one?
It was balanced on this machine. The one thing that we do, and I don't see it offhand, is we actually bring in a center pedestal. So we put in
for the center support
a third cross section here,
right,
where we physically mount that center bearing just like it's being mounted in the vehicle again, and we measure acceleration data on that center pedestal.
So that's a good segue to talk about this. So when you put the center support, right, you ensured that it was absolutely in line with the output shaft from the transmission.
Yeah.
Right? So there's almost no angle there.
There is zero misalignment side to side.
Okay,
it is
how about
100%
vertically?
straight. Vertically, we shimmed it so it was it's usually less than 0.1 degrees.
Okay.
We use a hardened wash
Downward
or a
angle?
hardened stack
Is
so
it a
that
down-
it has no angle whatsoever.
Okay.
That's where we found that the CTSV has a couple of degrees draft angle
Right.
engineered into the center bearing, because when we put it all up and we had the drive shaft at 0 degree angle, we noticed that center bearing had a little bit of a canter to it.
I see.
And that's when we talked with JXB.
And he confirmed that that's
And he
basically...
confirmed that it's the same way in the vehicle.
Yes, yes.
So-
Okay. So the one thing that I want to take away from this is when we, the average Joes, taking these great drive shafts that you make and putting them up in our V1s, right? How do we ensure we set ourselves up for success? Because this takes us back through all the discussion we had in your office talking about shimming, centering, and so on. How can we best ensure that we set up our drive shaft for the best result?
And what you talked about, hard mounting the ends to make sure that center bearing's in the right position is a decent way to do that.
That's a good start.
Measuring, using the Tremec app to make sure that angles are where we would expect them to be. And it may take a little shim to get those angles right at that center bearing. Those are all steps that need to be taken to ensure that you get the optimum setup. If you try and take shortcuts, you've done it yourself with trial and error. You put it in, you got where you thought it was best.
It's not a horrible way to do it.
No, it isn't.
Especially if you do it temporarily, like you just follow the factory procedure of not fixing the center support to the very end, right? You don't want to fix the center support first. You mount the front, you mount the rear, right? You tighten those bolts, and then you kind of like see where's the natural resting place of the center support. Secondly, take it for a test drive, right? See if there's any vibrations that happens. If there's no vibrations, you pretty much done your job, right?
Yep.
The drive shaft doesn't lie. And then you can start introducing shims at a small increment on both sides until that's not a wrong way to do it, if you ask me.
Not by any means. It's just a little more time consuming.
It's a little bit more time consuming, but not that much if you ask me. You know, it takes like usually 2 or 3 times to test it, because you don't have to remove the drive shaft to do that. All you're doing is just loosening the center support bolts.
Taking a fastener out and putting a
it's
shim
just
in.
2 bolts out, introducing more shims and putting. That's really not a horrible way to do it, if you ask me.
No, not at all.
But
not at all.
There are other misalignment factors that could be at play here. You know, let's think about this from the vehicle perspective. You have the front subframe, you have the rear subframe, right? Could it be that in these vehicles there's a way where maybe this subframe could be tilted a little bit to the right, this one a little bit to the left? How can we ensure that that's not happening? Even though it's a little bit complicated question, you know.
It becomes very difficult to do to ensure that that's not happening. One way would be to set a known reference point and take measurements off of that reference point, something that is going to be very parallel or perpendicular to your axes of rotation for the front and rear wheels. And then you can, that's how we measure for NASCAR. Is it's set up on a pull down plate, and we have the front center line of the wheel, the rear center line of the wheel, and we measure off of that to make sure that rear end isn't over too far.
Right.
Or in that case, because of track bar movement, we want it to be a little off so that when it moves for track bar, it compensates for that.
It does maybe have to do with the fact that NASCAR cars tend to do a lot of left turns?
That's right. That's why they have that track bar.
I see.
To help it with left turns.
Okay.
And in the CTSV case, you want it to be as straight as possible to start.
Right.
You don't want twist in those elements.
And my thought process has been, if I can't jerry-rig a fixture on my own to help me align things, I was considering that maybe once I have, if I put that shaft in and I still have some issues beyond the shaft itself, maybe it's a good idea to go to a body shop, Maybe they have some fixtures perhaps that help you, hey, check, is this subframe and that subframe aligned properly? Is this flange and that flange? What do you think about that? Do you know if vehicle body shops maybe?
They might have some resources there that could help with some of that to make sure that those subframes are properly oriented.
Because-
I would expect that you would see it in alignment.
Yeah.
If your alignment was slightly off, you're getting unusual wear.
So when you're
to the
doing your
rear
wheel
tires.
alignment,
Yes.
yes, it makes sense.
That would be another good place.
That is a very
look at.
important point we didn't discuss, is that, you know, if your alignments are wacky to begin with, you don't need to look at your drive shafts first for this then.
No.
You need to sort out those problems first. So it's very good, important point. I know last time I've had my alignment was probably maybe 2 years ago, but it's not a bad idea to check that your alignment is still fine before you start hunting for issues with your driveline.
Yeah.
Yeah. Because again, if your subframes are canted a lot this way or that way, it will show up in your alignment first. That's a very good point.
And it will show up in the drive shaft as well as being a compound angle, and it may cause a small amount of vibration, but it's not because of the drive shaft being out of position. It's because of that subframe being out of position.
Yeah, yeah. And one of the reasons why I haven't touched my subframes when troubleshooting drive shaft issues is because I know if I touch my subframes, I will be messing with my alignment, you know, instantly. I know it. So that is maybe perhaps an investigation I will undertake myself. This is beyond your area of work, but we thought we'd pick your brain on that. So anything else we want to see in the shop?
That's really
this
the
is
lion's share of it. That's what gets us to a finished product.
Can we see the one last thing? Can you show me the Audi RS3 two-piece drive shafts that I saw first time I came to your shop?
I don't have any.
don't have any?
I sold out.
Okay.
So I literally shipped the last one.
I remember last time
week.
over there. Yeah.
Yeah.
And that was one of the things that we said, you look, since we can do this, we could definitely do this for the V1. So maybe next time I'm here, we can talk about it. But Steve, thank you very much. We talked about PDE. We talked about your history and your experience. Then thank you for fielding the questions from the V1 owners. And then we went over the construction of the very first drive shaft from PDE for the V1, and hopefully one out of many to come.
One of many to go.
Absolutely. So I'm very excited. Steve is excited, and I hope you're excited too. Thank you very much for your time, and we'll see you guys on the next episode of our show. Have a good day.
Have a good day.